Hello and welcome back to Paleocast. My name is Liz Martin Silverstone and this is episode 112 on Extinction of the Dinosaurs. Today I'm speaking with Dr Alessandro Chiarenza, a research associate at the Imperial College London, about his new study on the drivers of dinosaur extinction at the end of the Cretaceous. This is some work that Alessandro did during his PhD, using climate and habitat modelling to understand what really caused the extinction of dinosaurs. So this is a little bit different than traditional dinosaur extinction papers. As always, there are a few images to go along with the episode, so make sure you check them out on our website. Finally, please share and give it a like on social media, and thank you for all of your positive reviews and feedback. We really do appreciate it. We don't really have any announcements today, so without further ado, we hope you enjoy this episode. So today I'm speaking with Dr. Alessandro Chiarenza about his recent paper in PNAS on the extinction of dinosaurs, which was part of his PhD at Imperial College London. Hi, Ale, and thank you for speaking with me today.
Hi, Liz. Thanks for the chat and your interest.
Can you start off by giving us a little bit of your background and how you ended up working on dinosaur extinction?
Sure. So I'm a vertebrate paleontologist, and I started my PhD, as you mentioned, at Imperial College London, but wasn't really going to focus on dinosaur extinction. That eventually happened. So my supervisors were interested into applying data from the Paleobiology Database, big biodiversity questions, and try to combine together not only this data from the fossil record, but also data from as outputs of general circulation models, like these big models that reproduce the climatic conditions in past times. And eventually, just because the dinosaur record seems to be better sampled and more accessible, let's say, also for these kind of studies towards the late Cretaceous, I ended up working on the, diversity trends towards the end of the Cretaceous, and that naturally evolved into something on the extinction. So I'm one of these persons that wasn't really keen or didn't have an interest on dinosaur extinction, and definitely started off with different interests, more on classic paleontology, not only topics, but also methodologies like phylogenetics and comparative anatomy. But then eventually, I'm really glad that my supervisors trained me and gave me this opportunity, because that definitely expanded my mindset, not only as a scholar, as a student, but also as a scientist, starting off with the details and the very subtle details of a scrap of fossil, and then eventually expanding that to the big picture. It's quite satisfying, and having done before Master of Science in Evolutionary Biology, I started having some skills that were analytical, but of course with my PhD I had the chance to expand them more, and getting a wider skill set right now. So I'm glad.
Yeah, it sounds really cool. Well, we're going to talk about particularly this paper that just came out. So congratulations on the new paper.
Thank you.
And this paper is looking specifically at the drivers of the end-Cretaceous dinosaur extinction. But this is a kind of popular idea, or there has been a sort of popular idea that this question has really already been answered. I think a lot of, the general public, if you say to them what happened at the end of the Cretaceous, they all think they know what happened and why dinosaurs went extinct. So can you explain a little bit about the background and the two main hypotheses that we have for the end Cretaceous extinction?
Sure. So, yeah, as you say, this is quite a very popular theme, not only in science, but also in pop culture. Exactly 40 years ago in June, a paper was published in Science, and basically the Alvarez and a team of other fellow scientists, they basically proposed from data on the stratigraphy of some areas in Europe, and that some asteroid at some point hit Earth, and that matches with the extinction of many life forms 66 million years ago. And because of the abundance of rocks that seems rich in minerals coming from the outer solar system, so outside Earth, and particularly from asteroids, they proposed that Actually, the extinction might have been caused in somehow by a big rock hitting our planet and causing a lot of mess to our environment and ecosystems eventually. But there was a competing hypothesis that, still was pursued and was researched and eventually proposed by many other people, that matching with these sort of same time intervals toward the end of the Cretaceous, you got this massive magmatic province, which at the time was covering India and the size of France, basically. So for thousands of years, you had this, continuous effusions and emissions of dust particles and magma in the surface of our planets that might have affected climate somehow. And some people suggested that the traces in our geological records of this event might have been the actual cause or the driver of these eventual climatic changes that caused the extinction of the dinosaurs. And recently in the last at least 15 years, maybe a couple of decades, there's sort of been kind of a run between these two competing hypotheses to be the one that has the upper end. And recently, there have been also a sort of a third way hypothesis about this, the sort of push and pulse hypothesis, where basically you have the asteroid as the final blow to already declining diversity that might have been affected somehow by the Deccan volcanisms. And so we had the chance to test this in our paper.
So how would volcanoes cause an extinction?
Yeah. So the proponents of the volcanoes or the volcanism as a driver of extinction suggest that by an emission of atmospheric reactive gases, particles from volcanoes, climate might have been affected somehow by these prolonged eruptions, basically, and causing global warmings, which have been suggested with a bracket of several degrees. So there's been lots of uncertainties based on the different studies and the different approach to try to constrain exactly what were these thermic excursion caused by the Deccan volcanisms. And they were suggested that basically just distressing the ecosystem, you would have caused a series of extinctions and potentially at some point becoming irreversible and causing the end-Cretaceous mass extinction, so affecting not only the dinosaurs but also other life forms, plants, other tetrapods, and marine life from plankton to fishes and marine reptiles.
How have the previous studies who have looked at the end-Cretaceous mass extinction, how have they looked at this question? What kind of data have they used?
Yeah. So one of the main sources of research into this area has probably been trying to constrain the dating of different events towards the end of the Cretaceous. So not only seeing how, for example, the diversity based on the fossil record was declining at the boundary. So this sort of geologic wall between the Maastrichtian, when dinosaurs were around, and the Paleocene in the Cenozoic, where dinosaurs weren't. But also eventually calibrating with detailed analysis and geochemical dating when these fingerprints of, let's say, the Deccan volcanisms with its either warming or cooling, depending on, again, the studies, or the cooling caused by the asteroid impacts, or in some cases, even the warming caused by the asteroid impacts. And so different studies have been trying to find different answers as long as, and the farther we were looking at more refined models and more refined techniques and even more refined tools for example, dating, and even more databases and more data generally for looking at these questions. But recently, because of the expansion in technology and computational power, many people have also tried to apply these general circulation models. So basically these virtual models based on grounded in physics, in the physics of our atmosphere, and inputting this information from the geological record and saying, we had, because of these agent, these emission of gases or this different thing happening to the atmosphere, how would that affect the atmosphere and the climate based on the, let's say, geographic extent of the continents that we had back in the Cretaceous. And so the more we were going forward with this line of research, and paleoclimatologists particularly cared that, the more refined reconstruction for what the models of climate might have been in response to these extinction events.
So specifically, what kind of data do you use in your study that's different from those done in the past?
Yeah, so my colleagues at the University of Bristol, and particularly Alex Farnsworth, Paul Valdez, and then Lunt, they used some of the up-to-date informations on the based on the geology and the geochemistry of the planet at that time and the different drivers, and then inputted them to an advanced technology and an advanced version of paleoclimatic models reproducing the conditions of the Cretaceous. And then eventually we reproduce different scenarios for each of these drivers. And so you could see what was happening, let's say, if only the asteroid was falling and the climate was being affected by it, but also what was happening if you forget the asteroid and only the volcanic eruptions were doing something. But then, and this is like something that also particularly new that my paleoclimatologist colleagues did, was using this information together, reproducing in a time series how the climate was evolving in time when both agents were being combined together in different scenarios. So having also to test the possibility, which is quite real, that both things were acting together.
Mm-hmm. You mentioned a lot about using models and paleoclimatic models. Can you explain a little bit what that means and kind of what goes into these models?
Yes. Yeah. So basically, since this is a very philosophical question, so since Galileo's time, the scientific method has been refined to try to reproduce what is going on in our planet and nature with mathematical models, with basically equations. And so the more our informations are and the more refined our mathematical tools are, the better we think we can not only reproduce something that we see in the current conditions of an experiment. So let's say, for example, the dynamic of our planet and climate right now, but also we can reproject that and look at what the same laws were acting in the past. And this eventually brings us for a neat point. As a paleontologist, we are used to see paleontology as an historical science, basically gaining information from a record that we are available of from millennia, millions of years in the past. But now we can also make experiments and see how they reconcile with these records, which is something that many modern biologists, for example, do and are able to do in their current experiments. But they have quite a limited confidence on how that might have been a version, let's say, of how the planet was behaving and nature was behaving back in time. So ultimately, this drives our science, paleontology, more towards the experimental science side.
I'm guessing the more data you have to put into the model, the better the model is going to be.
Yeah.
So this is...
Yes.
Sorry, go.
No, you're correct. And given, again, the advancement not only of the sources of big data, we have, for example, is a shout out to the Paleobiology Database, which is a very useful information. And we, for example, as former PhD student, many other fellows PhD students use it and help to refine it and help to improve it and enrich always the records or vet it. But also we have the push from the advancement of technology. We have machine learning algorithms and artificial intelligence algorithms that, for example, I partially use for this study that are going to improve our techniques, our predictions, our models. And, this can mean new frontiers for our discipline in the future.
This is why we haven't been able to do such a detailed study on the end-Cretaceous extinction the same way that you've done it before, because now we have more data and more models available and all of that.
Partially, yes.
So I guess now the big question, what killed the dinosaurs? What did you find out?
Yeah. One thing that is exactly that we had different versions of climatic models that were showing that asteroid was really bad and potentially causing a big nuclear winter or impact winter, and that volcanoes were doing different things to the atmosphere, potentially some warming and some cooling too. So let's test it. Let's see, as in lab experiments, what's going to drive what. And we added this ecological technique borrowed from conservation ecology, habitat suitability modeling, that, for example, taking these occurrences can create a model where the conditions of the climate are suitable for dinosaurs. And then we can apply, as in a switch, what's going to happen when you reproduce a scenario where you got a massive cooling caused by an impact, or, for example, a warming caused by massive volcanic eruptions, or seeing them both the agents acting together. And what we see is that, asteroid causes a blue screen of death for the dinosaurs. And while the volcanic eruptions don't seem to affect that largely the abiotic niches, these habitats for dinosaurs, and when they map together and you reproduce these different scenarios all together, you see that basically the asteroid does the blow, causes them to get extinct. But in scenarios where you don't have the Deccan volcanism active around this interval across the KPG boundary, you do see that it becomes bad. It becomes even worse. When they're active instead, they seem to somehow buffer the negative effects of the asteroid impact and quickening the extinction. And at the time that I was doing that, it seemed quite a counterintuitive hypothesis, to be honest. And we had to look closely at what the record was saying in the geology. But luckily, some other papers came out about, during the time that my thing was in review. And they were showing that the geological record actually does show something similar, seems to hint for something similar. For example, the recent Lyson et al. Paper in Science shows that after the KPG extinction, the recovery seems to be marked by 3 particular horizons of global warming. And given recent redating of the Deccan volcanisms, we now know that these global warming episodes matches with big volcanic pulses. And these not only affect the increase in diversity, for example, of mammals and their expansion in body size, but also the origination of important angiosperms groups. And similarly, for looking at something that affected, we know that the extinction also affected the sea. We see a similar thing in the microplankton, for example, given the studies of Hull et al. And it seems that, we may be approaching this sort of paradigm shift where, definitely the asteroid was a very bad day for not only the dinosaurs, but whole global ecosystems. But the Deccan eruptions that we're seeing as a sort of, this Shiva big punishment for the more strict ecosystems and the ecosystem biota actually may have helped out an extinction that might have resulted in a way worse scenario than it was.
That's really interesting. So one of the main things people thought caused the extinction actually maybe made it not as bad as it would have been otherwise.
Yeah, it's an interesting thought also, because ultimately, of course, this is, one of the first study that applies these sort of methodologies. But, dinosaurs are interesting. And of course, we pushed it for it also because the paleontologists on board of it are mostly specialized in dinosaurs. But ultimately, what's very interesting is what the biota did afterwards and how the recovery affected different environments, and how different groups, turtles, lizards, mammals, evolved eventually, radiated, and got their land niches back.
So you mentioned impact winter, and this is something that has been thrown around a lot when people talk about the asteroid and also the Deccan Traps. Can you explain a bit more about what that really means?
Yeah. So there are different studies, as I was saying before ours, that showed that putting together the constraints that we know from the geological records, and applying that to general circulation models. So the way atmospheres works around Maastrichtian and Cretaceous paleogeography, you do see this impact winter. And some people suggested that maybe even for centuries, you would have had drops in temperature up to minus 60 degrees Celsius, which is quite bad, of course. In our particular studies, we see that the bracket of the cooling goes around minus 30 to minus 40 degrees Celsius. And that lasts up to 3 decades. For 3 decades, you've got this massive drop in temperature, and then it starts rebounding. And in something like less than a century, you would have had a rebound to original pre-extinction conditions. And these, of course, are informations from reproducing these models, and they're definitely useful. But we have geochemical traces of that. We have stratigraphical traces, of course, of this event. So the best paper that I may think about documenting this sort of phenomenon, it's, I guess, the Johan Velkoop paper from, I think, 2014. So it's quite recent. And it looks at a classic stratigraphical series in Texas, the Brazos River, which documents the transition between the Cretaceous and the Paleocene. And they definitely have evidences of a short-term cooling event from geochemical fingerprinting. But recently, as I was mentioning before, some other people looked at the transition and the recovery, and they, of course, mapped also, isotopic information like osmium excursions or carbon excursion. They do show that there is a drastic drop in temperature right at the boundary, right when the iridium anomaly, this platinum group elements that seems to be abundant in asteroid and that we use to mark the KPG event, actually happened.
Normally when I think of what you can see in the geological record, I don't think of being able to see something that was a 30-year or 3-decade kind of event. So it's impressive that you can actually get these geochemical signatures from such a short period of time.
Yeah, that's true. Although, again, this is a model and it's definitely useful, but likely it's wrong. I mean, we know that definitely many models are useful for doing quantitative studies, but we can't say 100%, okay, that must have lasted for 1 decade or 2 decades. We definitely have this sort of signal from our models, and it kind of matches in somehow what we see in the records, but it might have lasted for hundreds of years. But ultimately, given that stuff survived, and given what we know from, for example, the rate of reproductions of what these things that survived might have been, and I'm thinking of birds and I'm thinking of lizards, I think it's quite telling that the event might have lasted no more than a few decades, and maybe definitely not at the century scale. And being recorded, as you say, it's quite extraordinary. But if I had to bet somehow, I would bet for a shorter timed event rather than a more prolonged cooling.
So we're not looking at 1,000 years of cold, because I guess then pretty much everything would have died if that had really happened. You had mentioned briefly earlier about this sort of idea that dinosaurs were already in decline when this happened. And I know there's kind of the idea that some people think they were already dying off, and this was just kind of the final thing that actually pushed them over the edge. Did your study look at that at all, or see anything relevant to that hypothesis?
So definitely my research did not that last paper, but my former chapter that went up last year in Nature Communications. And I was looking particularly of how more prolonged timed events, like in a longer time scales related to climate, might have affected the diversity. And in that paper, we showed that definitely we don't see their abiotic niche being somehow affected by, let's say, some episodes of warming or cooling during the last 15 million years of the Cretaceous. But what do we see is the taphonomic window, basically the set of conditions that allows for fossils of vertebrates to be preserved in the geologic record. And we specifically looked at the North American one because it's a very well recorded one and very well sampled one. We see that this taphonomic window reduces through time, and we probably now have some signals not only from that study but also from another recent one that got published led by Chris Dean and Susie Maitland that I co-authored, that we do see a signal that some fossil bias, some preservational biases did affect strongly right before the extinction record, at least in North America. But of course, when we look at trends in biodiversity, we always obsess with a very rich, fossil-rich area. But we don't have to forget that the record of dinosaurs is very abundant worldwide. And of course, right now, because we have more research groups and more people working in places like where, for example, a few decades ago, you couldn't do research, like Africa, for example, many new things are coming out. And South America is doing great for sampling the many layers that are very close to the extinction. Europe, we have new dinosaurs in Europe, even in Italy, that used to be a region quite devoid of big fossil vertebrates and particularly dinosaurs. And what we may expect is that by looking at the different trends in different continents, we may see quite a different signal from what we were used to look at. And so some surprise may pop up. But one interesting thing that reconnects a little bit with my PNAS study is that if you look, for example, at a very nice fossil locality or subcontinent in the planet, which is India, many researchers in India have been doing great stuff for sampling the fossil records in between the layers of the eruptions. So you got levels of eruptions in the Deccan, and then you got fossil beds. And in these fossil beds, you find not only dinosaurs, but also lizards, frogs, also surprisingly fossil egg fragments from these ecosystems. And they then disappear because you got an eruption that's covering up the fossiliferous layers, but then they come back. And so one interesting thing is that if these things were in decline because of the volcanic eruptions, you wouldn't definitely find like a continuous rebunding up until they get wiped out. And also don't forget that India back then was in the middle of the ocean because it was detached already from Africa, but also not yet colliding with Asia, main continent. So things couldn't migrate like this big animal. Think of a big titanosaur or a big abelisaur. So that's neat, I think.
Yeah, that is really interesting. I didn't realize that there were actually layers, like fossil-bearing layers in between Deccan Trap layers, which is really cool.
Yeah, it is.
So obviously your study and what you've done has focused on the dinosaur record, but we know that the extinction affected a lot more than just dinosaurs. Has there been anything similar that has looked at the non-dinosaurian record?
Not yet, I must say. It's a very important and interesting, eventually new area that could be explored with these methods, and I hope it will. We discussed that in our discussions section of the paper, what that might have meant for the recovery and for the extinction and the recovery of other life forms, particularly tetrapods, and how the marine record might match or our observation based on both dinosaurs and other invertebrates. But what is interesting is that many other researchers have shown with other set of records, particularly paleontological, but also the stratigraphy, that, for example, I'm citing now our friends Dan Field's paper that shows that the thermal radiation caused a wildfire right instantly at the boundary after the event, probably the asteroid-induced one. And this might have affected massively all the tree-dwelling birds. And that's why many entire groups of bird-dwelling animals, tree-dwelling birds got extinct. But ultimately shows that many of them that survived were coming from land-dwelling ancestors. And so we see a patterns of land animals recovering eventually and re-radiating after the extinction. And you see that in mammals as well. They start becoming big quite soon after the boundary, but probably we're starting off as a small-sized animals. And so that suggests that probably these animals must have been burrowing somewhere, maybe finding shelter from the cataclysmic events and climatic changes happening around. But interestingly, what we see, and that we could see that in our models, because we have the reproduction of how, for example, the riverbeds were being affected by these changes in temperature. We see that, for example, lakes and riverbeds have a higher thermal inertia for whatever big changes happens in the mainland or in the oceans. So similarly to what other people have been suggesting in the past, maybe fluvial lacustrine systems were offering the shelter, the ideal shelter for smaller size animals to survive. And that's how we got crocs and turtles today, maybe.
That's really interesting. I was thinking it would be cool to run the same sort of study that you did with animals that both went extinct and didn't, and see if they behave the same way with the models and what that would do. I think that'd be really cool.
Unfortunately, that was something that I couldn't do for a simple reason. We were discussing that before. The records of lizards and other similar animals like herps, mammals around this time in the Paleobiology Database is not that accurate. There are great people doing lots of work, and even some of my same cohorts, the PhD students at my time, I can mention Terry Clearly, for example, did a fantastic job improving this area of database, but you definitely need to work more in the future on refining, constraining the timing of these things that, just because probably they were the dinosaurs, people had just spent more time and they had more people curating this database. But, these will happen eventually, pretty soon, hopefully, and we could be able to test that on these fossils.
Is there anything in your study that changes or anything about what we think that asteroid actually was? I mean, we've obviously always thought it's the Chicxulub kind of Yucatan Peninsula. And is that still the thought today, or is there any other potential impacts?
Yeah, definitely there was, very bad, that was the asteroid, and that crater in Chicxulub is probably the one that is the scar that we have left in our planet from that event. Again, there are different studies, and one of my co-author, Joe Morgan at Imperial College, she's been leading plenty of studies looking at exactly the crater and what happens in the stratigraphy and the geophysics of the crater. And what emerges from her studies and studies from her group is that asteroid hit a very bad position, a very bad spot in our Earth crust, because it was a carbonate and sulfate rich region, causing the release of gigatons of amounts of massive amounts of debris and SO2 and climatically active gases. And who knows if the asteroid would have hit the Atlantic or somewhere in the middle of the ocean, not hitting actually. It probably would have been bad, and you would have had still lots of water vapor in the atmosphere, but maybe would have acted in a different way. We don't know. It's an interesting what if scenario, but this definitely was a very unfortunate event. And you definitely had hell on earth for one day, but what we show is that the actual causes of the extinction are how this event eventually affected for years to decades the planet. And so it's actually a good point for what we see today. We think that turning on and off some chimneys may be a good thing. Now we've been in a lockdown, and we are seeing the effects globally of how the air pollution is being affected by our inactivity. But we have no human experience of how these things may affect geochemically and all our environments for years and decades. And so we need to learn from that event, from the Chicxulub asteroid event, and try to take care of our planet and our climate. Yeah.
So I guess final question to finish this off is this the final nail in the coffin of the question of what killed the dinosaurs?
Well, I think I don't like to think about last nails in the coffin for science. When it comes to science, it's definitely a little bit of a push on a paradigm shift, as I was suggesting before. Like, instead of having these two big competing hypotheses, you're actually merging them together in a more dynamic and complex scenarios that is finding some some sort of validation also in the geological records. But what is important is that we have new tools on which we can use to explore these questions. And, it's definitely pushing into a different direction, which may be interesting, may actually suggest some more things that can be tested. Some of them will be improved, and we don't know. We now have to, it's telling that in the last few years, many more people from completely different groups have been starting moving to this sort of the acceptance that, the Alvarez theory is probably true, it's probably valid. There was an impact winter and that was catastrophic at a global scale and caused some damage and probably is behind the extinction. But there were other things happening around that maybe acted on the biodiversity differently than we expected. And I guess that we definitely are moving towards a more maybe elaborate and somewhat complex, but also more revealing and ultimately interesting answer on this extinction. So I guess, yeah, it's fun and interesting.
That's really cool. Well, thank you very much for talking with me, Alessandro.
Thank you to you, Liz.
Paleocast was brought to you by Dave Marshall and Liz Martin Silverstone, with contributions from Tom Fletcher, Vish Venkat, and Elsa Pancharoli. Music was composed by Patrick Kendall Smith. Paleocast was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on funding from you, the listeners. So, if you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programs, and follow us across social media platforms to get all the latest news. Finally, if you enjoy our podcast, then please explore all of our video content on YouTube and follow our other projects, the Virtual Natural History Museum and the Paleocast Gaming Network.